Thanks a lot. Okay, we can start this session with the first speaker. Is Professor Plamen Kochlukov from University of Campinas, and is going to talk on graded algebras that are sums of two homogeneous subalgebras. Okay.
Thank you, Daniela. And let us start then. One moment. So it is a great satisfaction for me to be the first speaker for this session today. And I would like to thank the organizers for their invitation, especially to Professors Lopatin and Kuzmin. And let us start. So you can see the title. I'm not going to repeat it. And let me stress that this is a joint work with Pedro Fagundes. He is somewhere here. I saw him. And so let us start. So I am going to talk about algebras with polynomial identities. So we have some field F, or you can consider sometimes an associative commutative unital ring. And A is a net algebra. I'll denote by f of x the free associative algebra that is freely generated by some countable set x of variables over the field f. And, let me stress, I do not require that this free associative algebra be unital. So we know that the elements of this free associative algebra can be viewed as polynomials, albeit in non-commutative variables. And a polynomial identity for a given algebra is a polynomial in the free associative algebra that vanishes for every substitution by elements of A. Clearly, the set of all PIs of all identities for A is an ideal, and it is closed under substitutions of the variable by any elements of the free associative algebra. So they are called T ideals or verbal ideals or ideals of identities. And here are some examples everybody knows. Every commutative algebra satisfies this well-known identity, the bracket. Then the upper triangular matrices n by n upper triangular matrices satisfy the identity that is a product of n commutators. And this is quite an easy exercise for linear algebra students. To prove that it satisfies this identity. Then, if we consider the associative algebra of 2 by 2 matrices, it satisfies this identity, which is commutator squared, commutes with everybody. It is called Hall identity, Wagner identity, several names. And the proof is also an easy exercise in linear algebra, elementary linear algebra, since if you get two square matrices, their commutator is a traceless matrix. It is quite clear. But if you specialize for 2 by 2 matrices, the characteristic polynomial will be of degree 2, and the coefficients are the trace and the determinant. Since the traceless matrix will satisfy simplified polynomial, Hamilton-Cayley polynomial, then it follows that if C is a traceless 2x2 matrix, then its square is a scalar matrix, and this finishes our argument. Then let us recall that the standard polynomial is the alternating sum of all n factorial possibilities for a monomial in n variables. And it's quite clear that if you have an n-dimensional algebra, then it will satisfy all standard identity standard polynomials Sk whenever k is larger than n. Since you can choose a basis, the basis will have n elements, so you necessarily, since the identity is multilinear, the polynomial is multilinear, you can consider substitutions by basic elements only, but then you have to repeat a basic element, and the sum is alternating, so it will vanish. And the well-known theorem due to Mitsura and Levitsky states that the n by n matrix algebra satisfies S2 times n and no identities of degree less than 2 times n. There are several proofs of this theorem, and clearly it is quite difficult to prove. I'm not going to enter into detail. Let me recall that if you take 2x2 matrices, this theorem is not really obvious, but sort of very easy. Since you take a basis of 2x2 matrices, but you start with the unit matrix, then S4 can be written as sums of products of two commutators in this way. And then you see, we have commutators. So if we substitute the identity matrix inside some of these commutators, then we get 0. So you cannot substitute the identity matrix, but you are left with 3 matrices only, and you have an alternating sum in 4 variables. So you have to repeat one of these basic elements. So it will vanish, and in fact, if you take 2x2 matrices, the identities are well known, and it is a theorem first proven by Razumyslov, then by Drensky, in its present form, in this form really, that the standard polynomial of degree 4 and that other identity I called Holler-Wagner identity, they generate everybody. And similar things are true in positive characteristic whenever the field is infinite, but you see the characteristic should not be 2, since if it is 2, it is an open problem. And let me only recall that if n is larger than 2, then it is not very well known, and it seems that it is very, very far from our understanding nowadays what the identities are for the n by n matrices. Okay, let us go to the opposite direction, since there are algebras that satisfy no identities. For example, the free associative algebra. Clearly, the monomials are linearly independent. They form a basis, and you cannot have a linear combination among the monomials. It is a bit more difficult, but not much more difficult, to prove that if you have an infinite dimensional vector space over F, then the algebra for endomorphism, all linear transformations in V, satisfies no polynomial identity. And now, let us consider such general questions. Let us suppose we are given several PI-algebras over some field F. how can we construct new PI-algebras starting from the given ones? So we have several PI-algebras, and we want to construct new algebras starting from the given ones. There is the well-known theorem of Birkhoff, the first half of the 20th century, that states that a class of algebras, V, is a variety of algebras if and only if it is closed under subalgebras, factor algebras, and direct products, possibly infinite direct products. So it holds, this theorem holds not only for algebras, but also for groups, for any algebraic systems where you can meaningfully define identity or identical relation. So it is a very general result, but as such, clearly it can hardly be of any serious practical use. So we have to look for something else. So another example, if you take two PI algebras A and B and form their direct sum, it is also PI. This is relatively easy to prove. So this example also lies on the trivial side of the things. And in fact, the first non-trivial example of such a construction is contained in a very well-known theorem of Amitai-Regev. This theorem was proved in 1972. If you have two PI algebras A and B over some field F, then their tensor product is also PI. And this theorem is rather important because of the consequences it provides and because of the methods employed in the proof. But let us mention one of the corollaries of this theorem. If you have a PI algebra that satisfies an identity of degree D, then its codimensions are exponentially bounded this way for every n. I am giving here a brief sketch of what the codimension of a PI algebra is. And I am going to pass here very fast. You take the span of all monomials in the letters x1, x2, up to xn. That is all n factorial monomials. You span a vector space. And in characteristic 0, you know that every T ideal is generated by its multilinear elements. So you have the intersection of the ideal with this vector space is Pn. Now the advantage is that Pn is a module over the symmetric group Sn, left module, and it is isomorphic to the regular module. So the intersection with I is a submodule, and you can take the quotient, which is also an Sn module. So the codimension is exactly the dimension of this quotient. And you study the quotient instead of the identities. So you study the non-identities because Pn is of dimension n factorial, and according to the theorem of Regev, the dimension of the quotient is exponentially bounded, so it is much less than the whole of Pn. And so let us consider another situation where you have an algebra which is a sum of two subalgebras, not necessarily direct. So in the 60s, Otto Kegel proved that in the case when BNC are nilpotent subalgebras, then A is also nilpotent. In fact, in that same paper, Kegel asked, albeit implicitly, the problem, the following problem, that what conditions one has to impose on BNC to guarantee that A is PI. Explicitly in 1994, Baidar and Mikhailov conjectured that if BNC are PI, then A is also PI. And let me recall that BNC commutative algebras does not imply A commutative. In fact, Bakhturin and Gembrun showed that A must be, okay, let us call it metabelian. Later on, Feltzenswald, Gembrun, and Leal found several conditions on BNC that guarantee the existence of an identity in A. Kepchik and Puchilovsky showed that in the case when B satisfies an identity and C is nil of bounded index, then A is also PI. And the same people developed in a series of papers some kind of a structure for rings that are sums of two subrings. And in several years ago, Kepchik solved in the affirmative the question whether A is PI. In fact, he obtained more general results. You take A, B, and C simply rings, not necessarily algebras. That is algebras over the integers. And the theorem is that if A is a sum of two subrings, if B and C are PI, then A is also PI. Okay, if you have a ring, then it is PI. What does it mean? It has to take integer coefficients of your polynomials, and you have to take at least one of these coefficients to be 1 or minus 1. And now, another topic, taken algebra in A and a group G. You see here the definitions of a G-graded algebra. This is a very well-known notion. In the same way, you can define a grading by some monoid. And here you see some examples. The first is the trivial grading. G is arbitrary, and you concentrate everybody in the neutral component. Okay, not very interesting as a grading, since you have no gradings, in fact. Then the second example is the well-known one from the probably high school or a bit earlier. The polynomial algebra in one variable is graded by the integers. And you can define the same grading for the polynomials in several variables. Then let us consider something a bit less trivial. Take the cyclic group of order n, and A, the matrix algebra of order n. Then put the vector space AG to be the span of all matrix units where the difference of the indices is equal to G mod n. This is a grading. It can be checked easily. It is the natural grading. Now, another grading condemned by n matrices, this time by the direct product of two copies of Zn. you take two matrices, specific matrices X and Y, given here, and then you take a pair of elements of the N, and you put as AG the span of this product, that is, it is one-dimensional, and it can be seen easily that this equality holds. So, this justifies that this determines really a grading on the N matrices. Then, if you take the group algebra of a group G, it is naturally graded by G. And these two gradings are interesting because you see, if you take a homogeneous element, which is non-zero, it is invertible. These are the so-called division gradings. And now another grading, very important one as well. Take the cyclic group of order 2 and take the infinite dimensional Grassmann algebra E. Then you can split it into direct sum of two vector subspaces, its center E0 and E1, the anti-commutative part of it. Okay, these are the so-called superalgebras in the associative setting. And since I'm not going to need very much this stuff, I'll skip it. Now let me recall. Vector subspace of an algebra, graded algebra, is called graded or homogeneous. It is the usual definition we know from the first courses in algebra. In the same manner, you define a graded subalgebra or graded ideal or homogeneous. And now, if we want to study graded identities, first we have to define the free object. And this is constructed as follows. You take, for every element of G, infinite set of variables. Then you take the disjoint union of these sets. In form of free associative algebra, it is naturally graded by assigning degree G to the variables of xg. And one of the manners of denoting this algebra is this one, the free G-graded algebra. It is free in the usual sense that you can extend to homomorphisms every mapping from the generators to a given algebra, graded by the same group. And now a question. Why do we want to study graded identities? And here you see several reasons for this. The first one, okay, it is clear, but what is behind that? If you have a graded algebra, you can study and separate its homogeneous components. And the homogeneous components, they are not the whole algebra, they are smaller. If A is a graded algebra, in addition, you have some additional structure that makes it easier to study. And let us return to the n by n matrices. We already discussed that we do not know the identities for Mn unless n is 1 or 2. But the graded identities for the natural grading are known for every n. The remaining grading I discussed, that is, there are several other gradings on the matrix algebra, but the grading, which is a division grading by the Zn times Zn, its identities are also known. And the question we will be discussing today is the following. Take an algebra graded by a group G and take two homogeneous subalgebras whose sum is the whole algebraic. So if B and C satisfy graded identities, can we affirm that A satisfies 1? And here some partial results. The first one is sort of straightforward. You suppose B and C satisfy graded identities, but where only neutral variables appear. Then A must be PI. Not only graded, but PI. And this follows from the well-known theorem by Bahturin, Bruno, and Riley. That states that if you have a finite group, an algebra that is graded by this finite group, and you have an identity, a graded identity in neutral variables, then the whole algebra is PI. In fact, they give also a limit for the degree of the identity. Another result, if you have a group and you have a class A of graded algebras that are closed under graded images and direct powers. I mean infinite direct powers. And if every graded prime algebra in A possesses a non-trivial homogeneous ideal that satisfies a graded identity, then A is a class of graded PI algebras. That's algebras that satisfy graded identities. Graded prime is the usual notion that if you have two homogeneous ideals and their product is zero, then at least one of them is zero. And as a corollary, you have the following fact. If you take a graded algebra, which is the sum of two subalgebras, but B must be homogeneous ideal, non-zero, and C only a subalgebra, where B and C satisfy some graded identities, then A also does. And for the proof, you can do the following first. This fact is known well known when there is no grading at all. If you have an algebra that satisfies no identities, then you can take a direct power away, an appropriate graded direct power, and you can find inside it a free algebra. In the graded case, the proof is not very different. And the second point is that you have a homogeneous left or right ideal in a free graded algebra, then it will satisfy no identities, no graded identity. Further, let me recall the notion of a semi-identity. Consider once again this situation. A is a sum of two subalgebras, homogeneous. Then for each G, you have that AG is the sum of the corresponding homogeneous components. Then you assign three variables corresponding to each one of BG and CG. And then you take this to be Y and Z correspondingly. Then make the unions, the joint unions, and form the free graded algebra. And then you take x g as the sum of the corresponding y and z. And form the corresponding graded algebra. It is inside this larger one. And you take a polynomial depending on the variables y and z. Then you call it semi-identity for A. If it vanishes whenever you substitute the y's by elements of B and the z with elements of C. Okay, you call a graded semi-identity trivial if it is a graded identity. And let us give an example, which might be useful later on. Take a non-unital algebra and let it be the sum of a subalgebra and an ideal, and you can take, in fact, the three associative algebra non-unital. S1 puts everybody that do not contain x1, and S2, okay, the subalgebra that contains x1 in each of the monomials. So S2 is an ideal. Then take A as this algebra and Z2 grading in this form, the diagonal of diagonal. So then A will be the sum of B and C, where B is this algebra you put on the diagonal elements of S1 only, of diagonal 0, and C is this one. B and C are homogeneous. Clearly C is an ideal. Then you have for A the following non-trivial graded semi-identity. And let us recall another notion. You take homogeneous variables and you define such a polynomial which is linear in these variables, and it is this sum where you see the x's are fixed, that is, their positions are fixed, and you permute the y's and with some coefficients. Okay, this is sort of a generalization of the so-called sparse identities, or in the end, they generalize the Capellian polynomials. And here, a theorem, take A as a sum of two homogeneous subalgebras, and suppose B satisfies some graded semi-identity of degree D1. And pay attention here, the degrees. And if the neutral component of C satisfies an ordinary identity of degree D2, then A is graded PI, satisfies a multilinear graded identity of degree N in homogeneous variables of degree G, and you have a limit for N. It is this large number. And now you may ask yourself, why all this hassle? Why you bother with such partial results? Probably it might be better to try and prove the general result, Kepchik-like, But let me recall that Kepchik theorem relies on the structure theory of associative rings and graded. And it is well developed. On the other hand, in the graded case, the structure theory is sort of radicals, primitive and so on. Modules is reasonably well developed, but not exactly to the completeness of the ordinary case. And there are several differences. Some of them are in the graded division case. Since in the case of division algebras, we know that the things are more or less clear in the ungraded case, but in the graded, the things are complicated. So I'm not going to enter much into details since I'm sort of short of time. And the final argument is that Kepchik theorem fails in general for the graded case. So you take the free associative algebra f of x, for short denoted by D. Take then the 2 by 2 matrices over D and denoted by A. So I'll define Z2 grading, the usual one on the diagonal of diagonal. And then you take two subalgebras of A, B and C, like okay, one is upper triangular, the other is lower triangular. Then these are homogeneous. Clearly, A is the sum of these two. But B and C satisfy the following identity. If you take two variables of degree 1 and multiply them, you get 0. It is clear since you have only entries at position 1, 1, or 1, 2, beg pardon, or at position 2, 1. And if you multiply two of these, then they vanish. So A is not PI, clearly it contains a free subalgebra. B and C, for the same reason, are not PI, but B and C are graded PI. And A satisfies no graded identity either. So it might be transferred to direct sum, to the Lie case as well. And in order not to exaggerate, let me thank you for the attention.
Thanks. Any questions or comments?
Well, I have one question.
Yeah.
Okay. Plamen, I have the following question. If we have that algebra B, let's say, satisfies some graded identity of some degree, and C satisfies some graded identity of some degree, can we say something about degree of the algebra A? Well, in case, of course, when A has this graded identity, I mean, in case A is ideal.
In fact, I gave one of these examples. Probably I go back to show it. But nothing else I could say. Or I jumped it.
Example about semi-identities, yes?
Yeah.
But in case of identities?
Graded identities, you mean?
Yes, graded, of course.
Not that I am aware of. In fact, if you take the ordinary ungraded case, you can find some I think in Puchilovsky and Kepchik papers, some limits in some cases, but in general, nothing. Here. You see the...
Yes, but here is a semi-identity, yes?
Yeah. In general, I do not know of any limit, upper bound for the degree.
Okay.
Since, okay, most likely the situation will be something like the original proof of this theorem of Frege for the tensor product, that you give some estimation in terms of, okay, I have an identity for A, I have an identity for B. So when I make the tensor product, I'll take enough consequences, so in some degree, it will turn to be less than n factorial. But
Okay.
I am not aware of any upper bound for the identity. If you know that B and C satisfy identities of given degrees without any restriction.
Well, in case of Kepchik, let's say in classical case, there are some results of this kind, but obviously with a lot of restrictions, like a lot.
Yeah.
And additional conditions, there are some results, some partial results about it. In general, I don't know. Yes. Okay. Yeah.
More questions or comments? No? Okay, let's thank again Plamen. Thank you, Plamen.
So
we have 2 minutes left.